and take a look at what's in the book for heat transfer. Heat transfer starts on about page 203 and 204. Only 2 pages worth of stuff about it. I don't care if you recognize it as Fourier's law or not, but the rate of heat transfer depends on a factor called the thermal conductivity. Thermal conductivity's units will tell you exactly what else goes in the equation. So the rate of heat transfer, that's watts, or how many joules per second are being transferred. And thermal conductivity, K, is in units of, so we've got watts equals watt per meter degree Kelvin. So what do we need to get watt per meter degree Kelvin turned into watts? Well, we need to multiply by meters and we need to multiply by kelvins. So the meters come from the area of the wall divided by the distance you have to travel through the wall. So we've got K for a wall. We've got a distance we have to travel, which would be X. And for a given surface area A, that would be meters squared divided by meters, and that gives us our meters. And then delta T is, of course, where we get our K. So the units can kind of guide you, but to understanding how this equation makes sense. So you need a K value, you need a surface area of the wall, and you need a distance X through that material. Interesting question and a very helpful idea mentioned in the chat window there by Manuel. In the FE exam, yes, the questions for each topic are grouped together. I find that interesting because given the computer-based exams and whatnot, it would seem very easy for them to randomize the order of the questions. And they do change the exam and the way the exam works from time to time, but traditionally, yes, the exams have been organized in such a way that you sort of march right through your own exam specification in order. So not only are they sort of all grouped together, but they're in the order listed in the exam spec. Clearly, lots of questions borrow from more than one type of discipline, but a question aimed at heat transfer will be right after a question aimed at thermo. That sort of thing. So a simple little equation there. This Q does have a dot over it, so that's the rate of heat transfer. That's actually sort of joules per second or watts. That's why it's watts. This statement is basically identical to this. This is sort of a differential based on differentials for every marginal increase in temperature and every little bit of distance you travel through the wall, what's going on. Well, this is the more practical version of that statement, where we can actually just plug in a delta t instead of a dt, and a delta x, or length, instead of a little incremental bit. So this equation and that equation are functionally the same. This one just looks a little more practical. It is worth noting that as you progress from one side of the material to the other, if this temperature is 100 and that temperature is 0, if you get to the middle, you're guaranteed the temperature is going to be 50. So that's that incremental travel across the entire length L. If you broke this into little tiny parcels of little tiny lengths L, you'd find the same rate of temperature decrease across every little incremental bit. So the temperature profile through a chunk of insulation, for example, is a straight line. And then if you switch to a different material, then maybe it's got a different rate. So it'll have a different straight line for the next material.